Our next speaker is Bill Bottke, who's going to talk to us about a possible surge in impacts 2 billion years ago.
Okay, let's see. Okay, so I'm going to try to give you a sort of a prospectus. This is an interesting concept. I think it's got a lot of promise, and I'd like to see where it goes. So here we go. Okay. Oops, how do you forward here? Oh, I'm sorry, I'm doing the wrong button. There we go. Okay, so I want to start talking a little bit about lunar chronology, like how do we get ages on the moon? So back in the day, we decided the best way to get ages on the moon was to send Jack Schmitt to the moon, and then we would count craters at the Apollo 17 site. And if we did this for a lot of different Apollo sites, we would ultimately get an age crater spatial density function, okay? So then what that means is if you have craters on a given portion of the moon, you can use this age function to tell you how old it is, okay? And that's what we actually did over here, and we have a number of different Apollo sites, okay? But there are some interesting issues that have happened since this given chronological function has come up. First of all, just sort of something to think about. Most of the regions on the moon that we've dated are older than about 3 billion years old, okay? So we have almost no information from between about 3 billion years and maybe about 800 million years or even less, right? There's just nothing there, okay? So that's an issue. We don't really know what's going on there. The second thing is that we've had some dramatic improvements in our imagery of the moon. So back in the day, people were counting craters either using lunar orbiter images or images actually from the command module on Apollo. But since then, we've gotten lunar reconnaissance orbiter images. The resolution is much better. The lighting angle is much easier to deal with. And so what's happened is people started to use those images to look at the Apollo terrains to see if the crater counts are identical or different. And in some cases, they're actually getting very different crater counts. Okay, so that has an implication for all sorts of things. So just to sort of illustrate this is a plot where I'm showing time before present in billions of years. And on the y-axis, I have this thing they call N1, which is just the number of kilometer-sized craters you have on a given region per square kilometer, okay? So that's N1. So these dots are from the sort of standard counts we have from Apollo, and that's how we got a given chronology. But Stuart Robbins in our group has recently recounted some of these crater sites, and he finds that some of them are different by as much as a factor of 2, okay? And so that generates a different chronology function, which might look something like this. Now, for older terrains, it may not matter that much, but for younger terrains, it gets very interesting. And let me just show you an example of this. So suppose you go to the moon and there's some terrain that's about a little bit over 3 billion years old, okay? So in the new chronology by this, you would actually shift that age by almost 1 billion years. It's got the same crater density, nothing has changed there, but the chronological function you're using is different. So the question is this billion-year shift real? Okay, is it actually true, or did we get it right in the old days? And how do you test this? Okay, short of going back and getting new samples. Okay, so I'm going to try to give you some rationale as to why I think the new chronology might make sense, because all of a sudden it's allowing me to take a lot of pieces and put them together, and they make more sense in the new chronology. So in a sense, I'm going to change this to why I think the new chronology is right. So here's some arguments for here, okay? None of this is lock solid. I'm just saying that as a caveat, but it's all kind of interesting. So earlier this year, we published a paper that looked at craters on the Earth. So we're going to start on looking at evidence for the Earth. It turns out that most of the craters we have on the Earth that are larger than about 20 kilometers are formed on these regions called cratons. They're fairly stable regions. They have undergone relatively little erosion. And where we find craters corresponds to about 10% of the Earth's surface, okay? But what's interesting is that most craters only go back about 650 million years. But then there's a few that go back that are older. They're almost 2 billion years old. These two craters are called Sudbury and Fredefort. And they're about the same size as the Chicxulub crater that we think killed the dinosaurs. Both are about 130 and 150 kilometers in size. Okay, so here's all the craters on the Earth plotted up on one given function. And you'll see again that almost all the craters that we see that are small sort of come to an end about 650 million years ago. And for a long time, this was sort of gradual erosion and you're getting rid of the craters and the rest. But we've re-looked a lot of these terrains. We can say a lot of this. I don't have time to go into this. But ultimately, there's a new idea in here that a lot of the craters we see simply haven't been very eroded. But about 650 million years ago is what we believe now happened in Earth history. They call this a global glaciation event, or something that's called Snowball Earth. This event produced kilometers of erosion on all the continents and sent a lot of this sediment and the rest to the ocean floor. Okay, there's geologic evidence for this, there's geochemical evidence for this, and all the rest. But what this would have done is gotten rid of all the small craters. But you'll notice there's two craters that sort of survived this. Sudbury and Fredefort. And so the question is, why are they there? We think the reason is because they're so big, they're very hard to erode. Okay, a few kilometers of erosion will not get rid of these craters. Okay, but then the question is, why are they sticking out there around 2 billion years ago or so? So what's going on? Because if you think about it this way, if the Earth has only 10% of its surface is stable, and you have one impact, then you have a 10% odds of hitting it, okay? But if you have two impactors, the odds that both are gonna hit that small bit of terrain is more like 10% times 10%, or it's 1%. So that's really low, okay? So another way you could ask this question is, does this mean there were more big impacts, okay? So if you take two impacts and you divide by 10% of the Earth, you end up with about 20 impacts. So this suggests that maybe back about the time we see Sudbury and Fredefort, there were a lot of other big things hitting the Earth. And how many is hard to say. You can see the big error bars here, but that's at least a simple calculation. So is there other evidence for this? And we think there might be. So when very big impacts hit the Earth, let's say at least the size of what made the Chicxulub crater, you also get what are called impact Sphero Beds. So what happens is a large impact hits, it creates a lot of molten material, it flies away from the impact site. In some cases it actually even goes to a slight Earth orbit before it descends again, and it makes these little droplets that look like chondrules, okay? And these beds of Sphero Beds can be dated and found even though the crater is long gone. We found several Sphero Beds and outcrops between about 1.8 and 2.1 billion years ago, and they're telling again about Chicxulub-sized craters that have gone away. We also find 4 between about 2.49 and 2.63. And if you just assume there's some kind of decay function between those two, you could actually get another 8 between about 2.1 and about 2.49 or so. So collectively, all the Sphero Beds are suggesting that maybe as many as 15 KT events were happening between about 1.8 and 2.6 billion years ago. And that's comparable to what the calculation I just did, okay? So what's really interesting about that is this, okay? So now all of a sudden we have a lot of things happening around 2 billion years ago or so. And this suggests if that many big things are happening on the Earth, something has to be happening on the moon. For every 20 things that hit the Earth, 1 hits the moon. So if this is right, we should have a big, young crater on the moon, and it should be obvious. It should be something that's, let's say, at least 150 kilometers in size or so. So the question is, do we have that? And the answer is maybe. Okay? So the last speaker did some of this work, so I want to give him credit here, Greenhagen et al. There's one particular crater that's really interesting, and it's called Volcanism crater. It's about 180 kilometers in size. It has a very healthy rock abundance, and rock abundance seems to be correspond to relative youth. Okay, most craters have rock abundance back to about 1 billion years or so, and then they kind of fade into the background. But not Volcanism crater. Even though it's supposedly 3 billion years old in the standard chronology, it's super rocky, and no one really understands why. There's some different rationales, but it's a mystery. The second thing that's interesting about Volcanism crater is if you look at the steepest slopes we have in the moon. So here's all the places where we have slopes greater than 45 degrees or so. So there's lots of different regions, but the one place that sticks out really prominently is Volcanism crater. And the people that did this paper, Kraslovsky and Head, suggested this could indicate this crater is actually Copernican age or Eratosthenean age, or for those that don't think about eras, that means the order of like 2 billion years old or so. Okay, so that's really interesting too. So let's assume for the moment that we actually had the age wrong, and this crater really is 2 billion years old. It turns out if we take the new chronology and we apply it to craters on top of Volcanism, we actually move it to right about there. So that would actually fit really well with all the other data sets we have. And so that says that maybe something big is happening on the moon about 2 billion years ago or so. Okay? In our group, we had Michellekerkhof has recently counted superposed craters on all the 50-kilometer craters we have on the moon. And if she uses the new chronology, she gets a big surge of events happening around 2 billion years ago. So again, this points in the direction that maybe something interesting is happening there. Okay? There's one more data set I want to bring up. This is sort of a problem that's been left over from the Apollo days, which I find has been fascinating to me ever since I was a grad student. So the Apollo 15 site has some samples. Most of these samples are older than about 3 billion years old or so, but there's some samples that were reset by some kind of event. Okay, this was noted long ago by Graham Ryder et al. But there was a recent paper by Grange et al. Where they looked at zircons at the Apollo 15 site, and they find that some of these zircons were reset at about 1.4 billion years ago and about 1.9 billion years ago or so. And the interpretation is that they probably had to be reset from ejecta from these two big craters, Eris and Atticulus. Okay? So the question is, what age are those craters? Okay, so just for reference, if you want to see how zircons might get reset, imagine Eris is forming and it's setting out hot ejecta and it's going all over the place and eventually it's bad, but that's how you reset samples at the Apollo 15 site. So if you look at Eris and you look at the crater age we would get from Michellekerkhof's work, we estimate an age of about 1.6 billion years. that matches really well the zircon age. For Articulus, it turns out we have lots and lots of secondaries on Articulus, so it's hard to get the age of it because Eris has contaminated it. But there's one small section without much ejecta, and that section, if you date it, has an age that's right about where the zircon age is. So all this seems to match really well, provided we use this new chronology. Okay, so there's a lot of interesting things going on here. Okay. For those that are wondering, like, well, what would be causing this big surge in impacts about 2 billion years ago? I won't get into this, I don't have time, but there's some very interesting and big asteroid families that are in the asteroid belt that may have broken up around this time. And they have been possibly been very good at delivering fragments to the inner solar system about this time. This all needs to be modeled in much more depth, but I think it actually could be an interesting possibility. And I'll just end on this. Okay, so for some of you in the audience are saying, well, this is all on impacts, why do we care? You know, that sort of thing. Some of you like volcanism. Okay, so here's the thing to think about. Okay, so right now our current model suggests that most of the volcanism on the moon happened about 3 billion years ago, and then it mostly ended. Okay, there's a little bit left, but not much. But if this chronology is correct, then a lot of the ages we have for volcanism at 3 billion years have to move to 2 billion years. And all of a sudden we start to see a big surge in volcanism around 2 billion years ago or so. So this could suggest that places like the Marius Hills and also the Aristarchus Plateau and the rest could have major components that are 2 billion years old, and for some reason they're having a big surge in volcanism the same time we're having a big surge in impacts. So the question is, I'm not claiming that's true, but it's an interesting possibility, and it would be nice to be able to check this in some fashion, okay? I'll also just point out that about 2 billion years ago on the Earth, there were all sorts of major events happening in astrobiology. We have the Great Oxidation Event, we have Snowball Earth events, we have lots of swings in oxygen, and this all may be happening at a time when we may be having a huge number of impacts around that time. So the moon may actually be really useful at informing us on how the evolution of the Earth has taken place, because all the data, the real constraints for this are on the moon, because that's, you know, it's hard to have erosion happen there and the rest. So there's all sorts of cool possibilities with this. And so I think with that, I'll put that up as a possibility, and I'll take what questions and what time I have left. So thank you.
Bill, favorite hobby horse again. There's some indication, some papers are thinking that Tsiolkovsky could possibly be of metallic origin, but also I work with Greg Baden, who they work at Sudbury. There's the big controversy that both Sudbury and Vredefort could have been metal or at least large metal content. If that is the case, then that might help narrow down or constrain your search for the asteroid families that provided the impacts. Absolutely. I didn't actually realize that we had much information. I think we have information on Sudbury. I don't know if we know much about Vredefort composition. And I didn't know we know anything about Tsiolkovsky. It's because it's on the far side. But yeah, there's some papers on that, and we're doing some work on it right now as well.
Send me an email with the references. Okay. I'd love to see it. Thank you.
Hey, Bill.
Hey.
Fantastic talk. I think there are indications that there are possibly 2 more impact craters elsewhere of about 2 billion year age. So one in northwest Scotland, and I think the other one possibly could be in India, but to be confirmed. So I think we should look into that. My question was that when you say big asteroid family, broke apart, and that's what was responsible, do you know which type of asteroid it could have been?
Okay, so the 2 families I mentioned, one is what we would say is probably an ordinary chondrite type family. The other one is a carbonaceous chondrite type family. But I would say that, I got to do I'd have to do that project to see whether they're viable sources or not. The ages are, the dynamical ages are about right. The family sizes are about right, but I got to do more work on that. So we have 2 possibilities, and it could be both contributed at some level.
It's just so that we can look for the geochemical signature.
Yeah, exactly.
Yeah, thank you.
So.
I think we need to move on.
Could, one quick, deep cores, Bill. I mentioned deep coring.
Yes.
We need to do that because we can get down to regolith that's 2 billion years old.
That would be awesome.